We now know how the logistic regression model works, but in order to actually fit our model, we need to choose a loss function. A natural choice might be the squared loss, which we've seemed to use over and over again in this class. And that's for good reason, but as we will soon figure out, it doesn't work so well in the logistic regression case. But anyways, let's suppose we stick with squared loss for now. Our empirical risk, or mean squared error here, looks something like this average of true labels, yi, minus sigma of xi transpose theta, all squared. Here, xi represents the ith row of our design matrix, or the ith observation. And so this is what our empirical risk looks like. And note here, we are not using any regularization, though we could and will in the next lecture. Let's try it out. Let's see what happens and go from there. So in this notebook, I've created this function, MSE loss single arg NBA. Now that's a mouthful, so what is it actually doing? Well, it takes in a guess for theta, and in this specific scenario, theta is just a single number, because our model thus far has only had a single feature. What it does is it takes in this choice of theta and returns the mean squared error for that choice of theta on our NBA dataset for the logistic regression model. So here I'm saying X is my list of field goal percentage differences. My observed Y values come from the one column of the game's data frame, and my predicted probabilities is the result of multiplying X with theta and passing that through the logistic or sigma function. And again, here X and theta are just single numbers, but more generally they can both be vectors. I then return the mean squared error of this choice. And so the reason I have written it in this particular way is so that I can use it with SciPy's optimize.minimize function, which you may have explored in a lab. Before we do that, let's plot what this loss surface looks like. On the x-axis, we have our choice of parameter, and on the y-axis, we have the mean squared error, or mean of our whatever our loss function is for this choice of parameter. You can see here that the mean squared error minimizing value of theta is somewhere between 20 and 40, but I can't really tell by eyeballing it where precisely it is. But have no fear, that's where minimize comes in. So scipy.optimize.minimize takes in a single argument function and tries to determine the arguments to that function that minimize its output. Along with the function itself, you need to specify an initial guess of what you think these arguments should be. And a pretty common initial guess is 0 or some randomly determined number, but we'll stick with 0 here. And this output tells us that this empirical risk is minimized when theta is equal to 29, so somewhere around here, which kind of makes sense. And now, my best sort of value of theta that minimizes mean squared error is 29.13, and if I plot sigma of 29.13 times x, you can see that it almost perfectly matches that red graph of averages that we saw before. So if you remember earlier in the notebook, we plotted x times 30, the best choice of theta when it comes to mean squared error is 29.13, but 30 was close enough. Anyways, it seemed like using mean squared error worked just fine here, but that isn't always the case. Here I have a toy dataset made up of randomly generated x and y values. This is what that toy dataset looks like. I have 5 observations, 3 belong to class 0 and 2 belong to class 1. What I will again do is create a single argument function that takes in a guess for theta and returns the mean squared error for that choice of theta. And then we will again sort of use minimize on this function and see what it gives us. And so if we call this function with theta is equal to 10, we get 0.32265 or whatever. We have no way of telling if that's good or not because, I have no idea what the actual optimal theta should be. Now here's where it gets interesting. We earlier plotted the loss surface of the NBA model, and things looked quite smooth. But let's take a look at the loss surface for this toy dataset, the logistic regression model, and squared loss as our loss function. Whoa. This loss surface does have a unique minimum, somewhere around theta is equal to minus 0.5, but it's clearly not convex. The definition of a convex function is a function where no secant line, which is a line drawn between 2 points on the function, crosses the function. All secant lines need to be on or above the function for it to be convex. But you can see here, if I sort of connect the dots between my point where my mouse is here and this point over here, that secant line is completely underneath the function, and so this is not convex. And so the implications of that is that numerical solvers like gradient descent will have a hard time converging on this minimum value. And whether or not we converge on this global minimum value depends on where we start our initial guess for theta to be. And so we're about to do that, but I want to give you an idea of what's about to happen. You can see in this flat region out here, the derivative of our empirical risk with respect to theta is very close to 0. And so if we start our initial guess for where we think theta is out here, our numerical solver will think that we've already reached the minimum because the gradient is so close to 0 that it will just stop right there. And that will prevent us from arriving at the true empirical risk minimizing value of theta. If you don't believe me, let's prove it. So let's first try calling minimize on this empirical risk with our initial guess for theta set equal to 0. So we're starting right around here. And so this will work just fine. We will end up at the true global minimum for theta, or very close to it. And it's minus 4.80, which roughly matches what we see in this picture. If we plot the resulting model for this choice of theta, the results look somewhat reasonable for this toy dataset. This pattern is quite atypical, but still, this sigmoid curve seems to fit the data as best as it can. If we instead start our initial guess for theta way out in that flat region, so at 500, so if we start off our optimization procedure right here, the resulting value for theta that scipy.optimize.minimize thinks is the minimum one is theta is equal to 500. The reason it didn't, move at all from here is because at this point, the gradient is so close to 0 that it thinks we're already at the minimum. And so that's problematic because when I plot sort of the resulting curve here, this result looks very different than the one where theta is equal to minus 4.8 or so. So, this is problematic. When our loss surface is not convex, wacky things like this can happen, and we're not really sure what the parameters we will get back from our numerical optimization routine will be. So the case where our loss surface is not convex is one we want to avoid. Here's another quick picture of an example of a mean squared error loss surface for a logistic regression model where we have both an intercept term and a single feature with a weight attached to it. And, this sort of pattern tends to appear quite a bit, where we have a flat region, and if we start our optimization routine out in this flat region, it, might not necessarily converge on the true empirical risk minimizing theta. Another issue with using squared loss for logistic regression is that the squared loss for a single observation is bounded to be between 0 and 1. Right? Yi, our true label, is either 0 or 1, and yi hat, our predicted probability, is a probability which is also between 0 and 1. And so the maximum possible value of this term is 1. And so this doesn't allow us to penalize bad predictions significantly enough. How this manifests itself in our loss surface is we get things like this. Here, 750 is far worse of a prediction than, say, 250, but their mean squared errors are roughly the same. So there's no way of differentiating between these two. We want our sort of empirical risk to increase as our predictions get worse and worse, and that doesn't really happen when our mean squared error is bounded between 0 and 1. And so what we will now do is set off on a quest to determine a new type of loss function that is better suited for, models where we are predicting probabilities.